January 1940, the Ross Ice Shelf. A 55-foot, 34-ton machine touches Antarctic snow for the first time and cannot move. Its 10-foot smooth tires spin against the very surface they were built to conquer. How did some of the most ambitious snow vehicles ever canceled fail? Not because they lacked engineering brilliance, but because reality exposed their blind spots? The answer begins with problems no blueprint predicted. The Pullman Company's Chicago factory floor became a scene of controlled chaos in the summer of 1939. Blueprints for a machine the size of a city bus, 55 feet from nose to tail and 10 feet high at the tires, were unfurled across drafting tables. Welders, machinists, and engineers worked in overlapping shifts, racing a wartime clock. The finished hull would weigh in at 34 tons, dwarfing any land vehicle previously sent to Antarctica. At the heart of the build were 4 smooth, 10-foot diameter tires, each custom fabricated by Firestone to spread the cruiser's massive weight across the snow. The drivetrain, a hybrid of twin gasoline engines and electric traction motors, was designed to deliver power to each wheel independently. Pullman's fabrication logs confirm the timeline, just 11 weeks from first steel cut to final assembly. The pace left no margin for error, but the ambition was clear. This was to be a laboratory, living quarters, and command post, all sealed within insulated walls. Inside, the cruiser offered bunks for 5, a galley, a cryogenic freezer, and a compact radio lab. Even a Labrador Husky had its own space. As the last weld cooled and the crew signed their names on the steel seam, the final checklists echoed the scale of the project. 6,000 gallons of fuel filled internal tanks. Every wire and bolt was logged in the fabrication ledger. The cruiser was rolled onto a waiting flat car, then loaded for its journey south. By January 1940, the engines roared to life on Antarctic ice, unleashing a machine that embodied the promise and the risk of translating vision into reality. On the Ross Ice Shelf, the Antarctic Snow Cruiser's promise unraveled almost as soon as its engines fired. The ground pressure, calculated at roughly 0.4 pounds per square inch, should have allowed this 34-ton colossus to float over soft snow. But the vast, smooth tires, 10 feet in diameter, could not translate flotation into forward motion. Instead, the cruiser skated atop the surface, its weight distributed too broadly to bite into the snowpack. Expedition logs from January 1940 recount repeated attempts to cross shallow drifts, only for the cruiser to slip sideways or stall entirely. Photographs from those first weeks capture the spectacle. A machine designed for conquest, immobilized by the very environment it sought to master. The engineering team, led by USAS commanders, tried every remedy they could devise. They deflated tires, added chains, even attempted to retrofit steel cleats, yet the cruiser's traction deficit persisted. Each failure was logged, each repair attempt consuming precious man-hours, over 150 per 100 kilometers, by the season's end. The cruiser's inability to generate shear traction, a direct consequence of its design, became a crisis not just of mobility, but of credibility. Scrutiny followed swiftly. In Washington, lawmakers convened hearings to question the project's value. A congressional transcript from early 1940 records a pointed exchange. "Gentlemen, a machine of this size, with such a ground pressure, should not be sliding backwards on snow," one committee member remarked, echoing the frustration of those watching from afar. Engineer E.J. Miller, under oath, admitted, "The 11-week construction window left insufficient time for full testing of the drivetrain under polar conditions." What began as a showcase of American ingenuity now faced the cold calculus of oversight. The cruiser, stranded and under investigation, became a symbol of the risks inherent in translating vision to reality, where every trade-off, from tire design to test schedules, could tip the balance between triumph and embarrassment. Kharkovchanka's story begins not with a blank sheet, but with the bones of the Soviet ATT artillery tractor, a machine already proven on the Eastern Front and the Siberian taiga. Soviet engineers at KHZ didn't simply repurpose the ATT, they reimagined it. The hull was stretched to over 8 meters, and the steel frame was rebuilt to carry a fully insulated living module, thick with cork and asbestos. This wasn't just a transport, it was a rolling outpost designed to keep a crew of 10 alive and working for weeks in the world's coldest desert. At the heart of the Kharkovchanka sat a V12 diesel engine, originally rated at 460 horsepower, but soon uprated to nearly 500 as field crews demanded more torque for hauling fuel, science gear, and sledges across the plateau. Factory test sheets from 1958 confirm these figures, showing a maximum torque of 2,200 Newton-meters and a cruising power draw that dwarfed any Western snowcat of the era. Soviet patent filings from the early 60s detail a unique hydraulic tensioner, an automatic system that adjusted track tension as the steel expanded and contracted in sub-zero temperatures. This innovation, cited in USSR patent number 1,445,620, was intended to keep the vehicle moving even when the mercury plunged below -40. The track assemblies themselves, over 1.5 meters wide with reinforced steel shoes, were designed to spread the Kharkovchanka's 30-ton mass over a greater area than any previous Soviet tractor. Engineers believed that this would allow the machine to float atop soft snow while maintaining the grip needed for steep climbs and long traverses. Production began in 1958, with the first 3 units shipped south by January 1959. Each vehicle was loaded with 4,500 liters of diesel and enough spares to last a full season, a testament to the expectation that these machines would not just survive Antarctica, but master it. For the KHTZ team, every design choice was a bet on supremacy, power, insulation, and self-sufficiency, all in a chassis that traced its lineage to the most durable Soviet hardware. The Kharkovchanka arrived on the ice as the most advanced over-snow vehicle the world had seen, its ambitions written into every weld and patent drawing. Fuel diaries from the Mirny and Vostok traverses reveal the daily arithmetic of survival inside the Kharkovchanka. Each machine carried a 4,500-liter diesel tank, a figure that promised self-sufficiency but quickly became a logistical anchor. Mechanics recorded fuel burns ranging from 45 to 70 liters per hour, depending on whether the vehicle was cruising across the plateau or hauling a full sledge uphill. That meant a practical endurance of just 480 kilometers before the tanks ran dry, a number that shrank further in deep snow or during engine idling to keep the cabin warm at -40. Crew notes describe the routine. Every few days, the convoy would halt beside a buried fuel drum, its position marked months earlier by a bamboo flag and a scrap of canvas. Refueling was a team effort, with hoses thawed over the galley stove and diesel pumped by hand through filters clogged with ice crystals. One mechanic wrote, "We measure progress not by kilometers, but by liters remaining. Every detour, every hour lost to repairs is another ration of fuel we can't afford to waste." The Kharkovchanka's ability to cross Antarctica depended as much on these hidden depots as on its V12 engine. Diaries recount the anxiety of watching the gauge dip toward empty, knowing that a missed cache meant a long wait for rescue. Museum displays today show the preserved cabin, but it is the penciled fuel logs and battered jerry cans that capture the real story, a vehicle engineered for autonomy, yet always tethered to the fragile lifeline of supply. In the end, the promise of unlimited range was undercut by the simple math of consumption and the harsh reality of a continent where every liter had to be hauled, cached, and accounted for. When Quebec's rural winters shut down roads in the 1930s, local planners turned to Bombardier's snow buses as a lifeline. City ledgers from Trois-Rivières and Sherbrooke confirm orders for 12 passenger machines, each designed to ferry children, mail, and groceries across unplowed routes. These buses, with their rear tracks and front skis, became a familiar sight in small towns, reliable if not luxurious, and capable of cutting through drifts that stranded ordinary trucks. But as the province invested in snowplows and road graders through the 1950s and the 1960s, the economics shifted. Annual audits show that by 1961, the cost to operate a snow bus was about 30% higher per kilometer than a conventional bus on a plowed road. Procurement records reveal a steady drop in municipal orders, and by the early 1970s, town councils began retiring their fleets. The snow bus, once essential, was quietly outpaced by infrastructure. Its obsolescence was written not in breakdowns, but in budget columns and maintenance logs. 3 lesser-known snow machines each reveal a different blind spot in over-snow vehicle design. The Swedish Active Snow Track, in production from 1957 to 1981, offered lightweight agility and a simple Volkswagen air-cooled engine. But its low ground pressure came at the cost of limited traction in deep powder, an issue that could not be solved once Volkswagen ended engine supply. The Theokol Imp, a 1960s turbine-powered snowcat, promised industrial muscle for oil fields and mountain passes, yet the turbine's appetite for fuel, burning through a gallon per kilowatt-hour, made it unsustainable for remote operations, and maintenance crews recorded high man-hours per 100 kilometers just to keep it running. The Rhino screw-propelled prototype, built in the early 1960s, attempted to sidestep wheels and tracks altogether. Its twin helical screws could float over drifts but lacked reliable steering. Test reports document the vehicle veering off course whenever it hit uneven snow, a flaw that ended the project after only 2 prototypes. Restoration teams and patent abstracts preserve these machines as reminders. Even outside the headline cases, every bold solution brought its own Achilles heel. Visionary engineering alone cannot outpace the realities of environment, logistics, and shifting economic priorities. Today's polar vehicles succeed not through spectacle, but by embracing efficiency, adaptability, and proven systems. The lesson endures. True progress means understanding the limits of ambition before the snow buries another dream. Subscribe for more deep dives into engineering history.